Hi, Chem 101 students, and welcome to the last lecture of the week. This is continuing our discussion on stoichiometry. In particular, we're going to deal with the slightly more complex situation where we have a limited amount of multiple reactants and trying to figure out how much product we could actually get from those reactants. So going back to the kitchen cooking example and the pancakes, we've got this pancake reaction, which is that 1 cup of flour reacts with 2 eggs, half a teaspoon of baking powder, and we get 5 pancakes out of that. Now, the issue is, let's say you're rummaging through your cupboard, you want to make as many pancakes as you can, but what do you got? Well, it turns out what you've got left in your cupboard is you got 3 cups of flour. In your fridge, you find 25, or you find, let's see, let's count them. 4, looks like 10 eggs. You got 10 eggs in your cabinet, and you've got 2 or 4 half teaspoons of baking powder. So actually, let's see, each one of these looks like it's probably each of these is a whole teaspoon. So imagine this. Okay, you've got this stuff in your cupboard. 1 cup of flour makes 5 pancakes. So we could figure out that 3 cups of flour would make 15 pancakes. So we have enough flour to make 15 pancakes. We've got enough eggs to make 25 pancakes. Okay, since we have 10 eggs. And we've got enough baking powder to make 40 pancakes, let's say, however much that is. We could figure it out. The point is that if we were actually going to use these ingredients to make pancakes, the actual number of pancakes that we would realistically be able to make is 15. We couldn't make any more than 15. We have enough eggs to make 25. We have enough baking powder to make 40, but we're not going to be making 40 pancakes because we only have enough flour to make 15. So that's how many are going to be made. What we would say here is that the flour is our limiting reactant. No matter how much of whatever else we have, if we only have 3 cups of flour, we can only make 15 pancakes. So what we do when we figure out how much product, like pancakes, we could make from our reactants is we figure out how much product each of these reactants could make if there was more than enough of everything else. And then whichever reactant can make the fewest of our product, that is how much of the product is actually made. And that reactant is referred to as the limiting reactant. And so theoretically here, we can make 15 pancakes. So that's the other thing we didn't talk about in the last lecture. We assume that every reaction is going to go perfect. But you guys know in real life, nothing goes perfect, right? Let's say you're making pancakes, okay? You're making your pancakes, and you burn 3 of them. So you mess that up, though that didn't get the right product. Then 1 falls on the floor. So instead of getting 15 pancakes out of your 3 cups of flour, you actually got 11. So our 15 pancakes was our theoretical yield. But really, we got 15 minus 4 that we messed up. So we got 11 pancakes realistically. So even though we had enough flour for 15 pancakes, and theoretically we could have made 15 pancakes, when we finished we only had 11. And so we can calculate what's known as a percent yield. So remember, percent is always, the percent of anything is the part over the whole times 100%. So in this case, the part is our 11 pancakes. That's the part, our actual yield. The whole, what we could have gotten, is our 15 pancakes. So we're going to be putting 11 pancakes divided by 15 pancakes times 100%. So here, the 11 pancakes, if we were doing chemistry, we'd call those the actual yield. And the 15 pancakes we would refer to as our theoretical yield. So our percent yield is going to be the percentage compared to our theoretical yield of what we actually got. So in this case, our percent yield is our part that we actually got, the 11 pancakes, divided by the whole theoretical yield that we could have got, 15 pancakes, and then times 100% to make it a percentage. And we can go ahead and calculate that. It would be 11 divided by 15, which equals 0.733, and then we multiply it times 100 to make it into percentage. So we get about 73%. So this situation that we've encountered where we get 73% yield for our pancakes, this happens in chemistry as well. Sometimes when you're running a reaction, there's no guarantee that you're only going to get the products you're looking for. Depending on the way the reaction goes, or depending what the reaction is, you won't always get 100% yield. This goes for cooking as well. You know, when you're basically, you don't even have to make any mistakes not to get 100% yield in cooking. You might be mixing the pancake batter in the bowl and you're trying to, you know, put it out onto the pan and stuff, but there's still some pancake batter left in the bowl that you didn't make into pancakes. You never get 100% yield for various reasons. And that's true in chemistry too, is you don't usually get 100% yield. There's always stuff left behind or stuff that didn't completely react, like you're cooking your pancakes and some of them overcooked, some of them undercooked and not real pancakes, you know. This can happen in chemical reactions as well. So we can calculate a percent yield for chemical reactions too. So notice the way we dealt with limiting reactant here with the recipe. We figured out how much product could be made from each of these reactants, and then we determined that whichever was the fewest amount, that's how much would actually be made. In this case, 15 pancakes we made, 3 cups of flour would be used, and not all the eggs and the baking powder were used. So likewise, when we do a chemical reaction, what we're going to do is we're going to use our 3 steps of stoichiometry to figure out how much product could be made from each reactant. And then we're going to figure out which of the reactants could make the least product. And then we'll know that that is the limiting reactant. So here we've got our 3 steps of stoichiometry. Step 1, step 2, step 3. And we're doing this for each of our reactants. Step 1, step 2, step 3. Same 3 steps, but we're just going to do it twice. How do we know that we have to do it twice? Well, in this example, we're given a reaction here. And then we're given the number of grams of not just one reactant, but 2 reactants. That's how you know you have a limiting reactant problem. You're given the amounts of more than one reactant. Because if you're only given one, the assumption is, well, I've got enough of everything else that I might need. But if you're given 2 amounts of reactants, then you know that one of them is going to run out first, most likely, and you have to figure out which one. So what we're going to do is we're going to start with our initial amounts of reactants. For sodium, that's 53.2 grams of sodium. That's what we're starting with here. For chlorine gas, Cl2, that's 65.8 grams. That's where we're starting there. So step 1 is always about converting the grams of our substance A. So here's our substance A, sodium in this case, or chlorine, to the moles of that substance A. So we're going to go for the mole. So remember, in step 1, we're always using the molar mass. So for a mole of sodium, that's going to weigh 22.99 grams. I can get that if I go to the periodic table here. 1 mole of sodium is 22.99 grams of sodium. Now for the chlorine, it's going to be a little bit more involved, because if we have 1 mole of Cl2, that contains 2 moles of Cl atoms, and each of those is, if we look at the periodic table, 35.45 grams of chlorine atoms is 1 mole of chlorine atoms. 35.45 grams is 1 mole of chlorine atoms. So that gives us 2 times 35.45, which is 70.9 grams. So 1 mole of CO2, which contains 2 moles of chlorine atoms, weighs 70.9 grams. So that's going to get us to our moles of these. Then we want to go from moles of our reactants to moles of our products. So in both of these cases, we're trying to figure out how much sodium chloride is made from these reactions. So we would use the balanced equation. For step 2, we use the balanced equation. And so for sodium, it's going to be 2 moles of sodium make 2 moles of sodium chloride. So this is going to be the conversion factor we use. 2 moles of sodium makes 2 moles of sodium chloride. For the chlorine, it's going to be 1 mole of chlorine makes 2 moles of sodium chloride. So that's what we're going to use for step 2. And that will give us the moles of sodium chloride. Finally, we need to figure out how many grams of sodium chloride that is. So in both cases, we're going to be using the molar mass of sodium chloride. So 1 mole of sodium chloride has 1 mole of sodium atoms in it and 1 mole of chlorine atoms in it. And we already figured out a mole of sodium atoms is 22.99 grams. And we're going to add that to a mole of chlorine atoms, which was 35.45 grams. These are from the periodic table. And so when we add those, we get, let's see, 4 here, and then carry the 1, a 4 here, carry the 1, an 8, and then a 5. 58.44 grams when we add those together. So 1 mole of NaCl equals 58.44 grams of NaCl. And so that's what we're going to use here, and that's going to take us from moles of NaCl to grams of NaCl. So now we've got all the conversion factor we need. Now we can actually calculate how many grams of sodium chloride each of these reactants could possibly make. Whichever makes the smallest amount, that determines what was your limiting reactant, and that determines the actual amount of sodium chloride that could be made. Okay, well, let's do the actual math. We're going to start with our sodium with the 53.2 grams. So we're going to write that here. And we're going to use our molar mass for sodium. It was, again, we put grams here, and it was 22.99 grams of sodium was 1 mole. Those are going to cancel. We get 1 mole of sodium. Next, step 2, we're going to use the balanced equation. We've got 2 moles of sodium make 2 moles of sodium chloride. So moles of sodium, the number that goes here, remember step 2 is the only time we use the balanced equation. We don't put a 2 here. No. 1 mole of sodium chloride weighs 22.99 grams. We're going to use the 2 is right here. 2 moles of sodium makes 2 moles of, or whoops, 2 moles, not 1. Mess that up. 2 moles of sodium chloride. Okay, 2 moles of sodium makes 2 moles of sodium chloride. Okay, next, we got to use the molar mass of sodium chloride to convert moles of sodium chloride to grams of sodium chloride. So just going back from the last slide, it was just let me write down the molar masses we got from the last slide. 1 mole of sodium was 22.99 grams of sodium. We had 1 mole of chlorine gas was 70.90 grams of chlorine gas, and we had 1 mole of sodium chloride was 58.44 grams of sodium chloride. So that's what we figured out on the last slide. And so again, what unit goes down here? Always same one that's right here, always the same. We gotta cancel them. Okay, we put what's here is the same as here. Now we're going to use our molar mass of sodium chloride. So 1 mole of sodium chloride is, and we cancel our moles of sodium chloride. And on the other side we put 58.44 grams of sodium chloride right there. And so now we calculate 53.2 divide by 22.99 times 2 since it's on the top, divide by 2 since the 2 is on the bottom, then times 58.44 since it's on the top. And we get the 3 sig figs, because the 53.2 has 3 sig figs, we get 135 grams of sodium chloride. And so that's how much sodium chloride could be produced from the 53.2 grams of sodium if there was more than enough chlorine. But we don't know if there's more than enough chlorine. That's what we got to figure out. So we got to figure out also how much sodium chloride could be made if all the chlorine gas was used. So we're going to do our 3 steps of stoichiometry again, but this time we're going to put the grams of chlorine down here. Grams of chlorine. Okay, we're going to convert grams of chlorine to moles of chlorine, so we need the molar mass of chlorine. We make sure The gram part goes on the bottom. Gram part has to go on the bottom so that we cancel. It has to. Okay. So what goes with that? 70.90 grams. 70.90 grams. Our grams cancel, and now we put the other side. 1 mole of chlorine gas. 1 mole of chlorine gas. Okay, done with step 1. Time for step 2, where we use the balanced equation. So for step 2, again, you don't even have to think about it. What goes down here? Don't think, just write. Same as here. Okay, you can think afterwards. After you know that these are going to cancel, then you think. But these better cancel. Okay, so what number is going to go with the chlorine? Well, since we're in step 2, we use the balanced equation. 1 mole of chlorine makes 2 moles of sodium chloride, because that's what we want to know about. Whoops, and that was supposed to be 2. 2. I flipped my 2 and my 1. Let's go back to where we were. Okay, 2 moles of sodium chloride. Okay, so now we're done with step 2. We just need step 3. We need to turn the moles of sodium chloride back to grams. And we use the molar mass we had right here. Again, moles of sodium chloride has to go here, so it cancels. 1 mole of sodium chloride, cancel your moles of sodium chloride. That is equal to 58.44 grams of sodium chloride. Now it's time to calculate. 65.8 divide by, since this is on the bottom, 70.9. Then the 2 is on the top, so we say times 2. We can ignore the 1s. We just have 58.44 left on the top, times 58.44 equals. And to 3 sig figs, since 65.8 has 3 sig figs, we have 108 grams of sodium chloride. So if we could use up all the sodium, we could make 134.5 grams of sodium chloride. But once we've made 108 grams of sodium chloride, all the chlorine gas is going to be used up. Doesn't matter that we have extra sodium. Just like in the pancakes, it didn't matter that we had extra eggs or extra baking powder. We were limited on our flour. Here we're limited on our chlorine. That's our limiting reactant. So we're only going to get 108 grams of sodium chloride because chlorine is the limiting reactant here. Okay. And so our theoretical yield now for sodium chloride is 108 grams. 100 grams, 8 grams we can make theoretically. Now let's do another percent yield calculation. So theoretically, we make 108 grams from our sodium and chlorine here. Not 135, 108 grams of sodium chloride. Then we're out of chlorine. So let's say we did this reaction and our actual yield was 86.4 grams of sodium chloride. Then our percent yield is going to be our part, our actual yield, which is the part, 86.4 grams, over our theoretical yield, which was 108 grams. And then we're going to make that a percentage by multiplying by 100%. So let's go ahead and calculate that. 86.4 divided by 108 equals 0.8, and then times 100 to make it a percent, and it's 80, and we should write this with 3 sig figs, so we would write 80.0%, because both of these have 3 sig figs, 86.4 and 108. And so that's the same answer I just wrote. So the part, the actual yield, over the whole, the theoretical yield, the whole of what you could get, times 100%. Okay. And so that's how you do a theoretical yield problem, and that's how you calculate percent yield. Now, what I'm going to do with this last problem, I have one last problem, and this is a big problem. What I wanted to do was kind of combine everything that we have learned over the past couple of weeks into one challenging problem. And so here is that problem. A solution that contains 3.48 grams of sodium phosphate is mixed with a solution that contains 2.63 grams of calcium chloride. 1.53 grams of precipitate is recovered. What is the precipitate and what is the percent yield? So in this problem, I have first of all written out the reactants as their names, which means to write the chemical equation, you're going to have to write the formula. So let's do that. First of all, these are both ionic compounds. I can tell because this has sodium, which is a metal. We look at our periodic table here, sodium is right here, it's a metal. And also, calcium is also a metal, it's right here. Now, sodium is group 1, so it makes positive 1 ions in the ionic compound. Calcium is group 2, so it makes positive 2 ions. And we also have a chloride ion. Chloride ions are negative 1 here. So we'll need to know that so we can write the formula. So sodium is positive 1, and hopefully by now you've got in your brain what phosphate is. Phosphate is PO4 negative 3. So you have to remember that in your brain. And so now we see that we've got 3 negatives but only 1 positive. So we're going to write this formula, we're going to need 2 more sodiums. That will give us 3 positives to go with our 3 negatives. So in writing our formula, we can now write our sodium phosphate. It's going to be Na3PO4. And it's in solution, it's in water, dissolved in water, so we call this aqueous. And we know that it's soluble because anything with a group 1 positive ion is soluble, so of course it dissolves in water, and we can write aqueous here. Next, our other reactant has calcium ions. So as we saw on the periodic table, calcium ions are positive 2. So we've got calcium here, which is positive 2. And we've got chloride ions. So the "ide" tells us that it's a monatomic negative ion. And so we can get the charge from the periodic table since it's monatomic, 1 atom. Since chlorine is in group 7, chloride ions are negative 1. Now, to get a neutral ionic compound, we're going to need 2 of these to give us 2 negatives to go with our 2 positives, right? And so our formula here is going to be CaCl2. And chlorides are generally soluble from the solubility rules. Calcium chloride is not an exception, only silver, lead, and mercury 1. So this will also be aqueous. I've also told you that this is in solution, dissolved, so we know that it is aqueous. And so now we can write, we need to write the products, and I didn't tell you the products because you can determine them yourself. That we're going to do a double switch. So the sodiums here are going to go with the chlorides, and the calcium is going to go with the phosphate. Okay, well, with sodium and chloride, it's pretty clear. We have positive 1 and negative 1. So the way we write this is just NaCl. And this is soluble in water because of the sodium and the chloride. So this is aqueous. So again, you may be thinking, but there's a 3 over here, right? No, that doesn't matter. Because when we write the formula, all we need to do is make sure that the charges are canceling, which they are here, positive 1, negative 1. Now to write my calcium phosphate, I'm going to need 3 calciums and 2 phosphates, because if I have 3 calciums, that gives me 6 positive charges. 2, 2, and 2, 6 positives. And if I have 2 phosphate, that gives me 6 negatives. So that way my charges cancel. That's why I have a 3 and a 2 there. And in terms of solubility, phosphates are generally insoluble, and calcium phosphate is not an exception. So this is going to be solid. This is our precipitate. So first, what is the precipitate? We were supposed to figure that out. and we have figured it out. The precipitate is the calcium phosphate. And so what we need to do is figure out how much calcium phosphate could be made from our reactants. Now, we do have a lot of work to do because we're going to have to calculate the molar masses. We also need to balance our chemical equation here. So in terms of balancing this chemical equation, I can use tip 3 here. So notice I have 2 phosphates over here. So if I want 2 phosphates on the left, I would want to write a 2 right here. So that will give me 2 times 1 phosphate, and here if I have a 1, that will give me 1 times 2 phosphates. Okay. Next, I could try to balance the sodiums. My sodiums over here are 2 times 3, that's 6 sodiums. So if I put a 6 here, that will give me 6 times 1, 6 sodiums. Now my calciums here on the right are 1 times 3, 3 calciums, so I would probably want to put a 3 here so that I have 3 times 1, 3 calciums. And then my chlorines are 3 times 2, that's 6, 6 times 1, that's 6. Okay, so we're good there. So we've got a balanced chemical equation that's all written. So as I told you before, sometimes that'll be the very first thing you have to do. We could not even start this problem until we could just write out the reaction. But now we've written it out. And so now notice we've got 2 reactants, the sodium phosphate right here and the calcium chloride. So we can write down what we're starting with these. We're starting with 3.48 grams of sodium phosphate. I'll write that right here. 3.48 grams of sodium phosphate. And we've got 2.63 grams of calcium chloride. And I'm actually going to move this a little bit lower. Oh no. I wish I would have. I'm gonna erase this and I'm gonna write it a little bit lower. I have lots of room here. I need some room at the top for reasons that I'll show you. Okay, so it's going to be 3.48 grams of sodium phosphate. And it's going to be 2.63 grams of calcium chloride. Okay. Now, our plan, remember the general plan here. Step 1, go from grams of your substance A, which in this case is sodium phosphate, and go for the mole. Go for moles of sodium phosphate. For that, we're going to need the molar mass of sodium phosphate. We haven't calculated it yet. Then, what we're interested in is how much precipitate that we had. So we're going to want to go from moles of sodium phosphate to moles of calcium phosphate. So that's step 2, right? This is step 1. Go for the mole. This is step 2. Go from moles of your first substance to moles of your next substance that you want to know about, which is the precipitate here, calcium phosphate. And then we want to go from moles of calcium phosphate finally to grams of calcium phosphate. That is step 3. Grams of calcium phosphate. And then likewise here we're doing a similar type of thing. We want to go from grams of calcium chloride to moles of calcium chloride to moles of what we're interested in, calcium phosphate, to grams of calcium phosphate. But to do all of this, we're going to need the molar masses of each of these things. Okay, so let's get those molar masses now. I'm going to calculate those molar masses. So first of all, we want the molar mass of sodium phosphate. We need that for step 1. So molar mass of sodium phosphate. This is going to have 3 moles of sodium. It's going to have 1 mole of phosphorus, and it's going to have 4 moles of oxygen. So 3 moles of sodium, 1 mole of phosphorus, 4 moles of oxygen. And so that's going to be for sodium. If we'll have to use the periodic table, 22.99 grams. 22.99 grams per mole. Okay. And for phosphorus, we're going to have 1 of those. Let's check that one out. It's 30.97 grams per mole. 30.97 grams per mole. And I'm going to get rid of my step 1, 2, 3 there just to give myself a little bit more room. So 30.97 grams per mole. And for oxygen, if we look, it's 16. So it's going to be 16 grams per mole. And then we're going to add those all up. Okay, so we're going to say 1 mole of sodium phosphate is how many grams? Well, let's add all of these up. So in our calculator here, 3 times 22.99 plus 1 times 30.97 plus 4 times 16. And that gives us 163.94 grams. Okay, 163.94 grams. Okay, so we've done it for sodium phosphate. Now we need to do this for for calcium chloride as well, because for step 1 of calcium chloride, we're going to go from grams to moles. So we're going to calculate that. 1 mole of calcium chloride is how many grams? Well, let's see. That contains 1 mole of calcium and 2 moles of chlorine. And so that's going to be for calcium. We go look it up. Calcium on the periodic table. It's right here. 40.08 grams if we round to 2 after. 40.08 grams. 40.08 grams. And then 2 times chlorine, which is 35.45. 35.45 grams. So if we add these all together, we're going to get 40.08 plus 2 times 35.45. And we get 110.98 grams. 110.98 grams. Lastly, we're going to need the molar mass for the calcium phosphate, because we're going to need to convert for both of these the moles of calcium phosphate to grams of calcium phosphate. And so let's write that out now. So we're going to have our 1 mole of calcium phosphate. And it may help you to count out the atoms to write this out on the side here, what is in it. So that is containing 3 calciums, which are 2 plus ions in there, and 2 phosphates, PO4 minus. So if we count up the atoms, this means we're going to have 3 moles of calcium, we're going to have 2 moles of phosphorus, and we're going to have 4 plus 4, 8 moles of oxygen. 8 moles of oxygen. And so for calcium, again, looking over from what we looked at already, 40.08 grams from the periodic table. For phosphorus, it was 30.97 grams. And for oxygen, it was 16.00 grams. So when we add all of these up, we get 3 times 40.08 plus 2 times 30.97 plus 8 times 16. And that is 310.18 grams. So now we have all the molar masses. We've got our balanced equation. We've got everything to do the 3 steps of stoichiometry now. So let's start. So the first step here is going to be to convert grams of sodium phosphate to moles of sodium phosphate. So as usual, we always put the same unit down here, right? Na3PO4 grams, because those need to cancel. And the number that's going with the grams is 163.94. 163.94. And our grams of sodium phosphate will cancel. And that is equal to 1 mole of sodium phosphate. So we're going to write that on the top. 1 mole sodium phosphate. Okay, next. Now we're going to do step 2. We need to go from moles of sodium phosphate to moles of calcium phosphate. For that, we use the balanced equation. And again, we always know what goes in the bottom. It's the same as what's on the top next to it. So this is going to be moles of sodium phosphate on the bottom, and on the number that's going to go with the moles of sodium phosphate in the balanced equation is 2 right here. I'm going to put it 2. And what we want to convert to is moles of calcium phosphate. So what we get is 1 mole of calcium phosphate right here. 1 mole of calcium phosphate. And our moles of sodium phosphate cancel. We have moles of calcium phosphate. Now finally, we convert moles of calcium phosphate to grams of calcium phosphate. So again, same old, just make sure what's on the bottom cancels. So we got to make sure moles of calcium phosphate are on the bottom here. And this is going to be, we're going to use the molar mass to go between moles and grams. Always the molar mass go between moles and grams. So 1 mole of calcium phosphate is 310.18 grams of calcium phosphate. So 1 mole of calcium phosphate rather is 310.18 grams of calcium phosphate. And our moles of calcium phosphate cancel, and we have grams of calcium phosphate, which is exactly what we wanted. And so now we can do our calculation. It's going to be 3.48 grams, and we're going to divide by this number, divide by 163.94, and then it's times 1. Make sure you divide by 2, okay? Don't press times before the 2. 2 is in the bottom, so we press divide by 2, okay? And then last 310.18 is on the top, so we write times 310.18 equals, and we get to 3 sig figs 3.29 grams of calcium phosphate. Okay, so we've got, now we know that 3.48 grams of sodium phosphate could make 3.29 grams of calcium phosphate in this reaction if there's plenty of calcium chloride. But we don't know if there is. Let's find out. So next we do the calcium chloride. So again, step 1, go for the mole. Convert grams of calcium chloride to moles of calcium chloride. So again, before you even turn your brain on, you don't got to turn your brain on yet. Just copy this unit down here. It has to be the same so that they cancel. And then we look for our molar mass of calcium chloride. It's right here. So the number that goes with the gram is 110.98 grams of calcium chloride, and that is the same as 1 mole of calcium chloride. Remember, your top and bottom of any conversion factor have to mean the same thing, right? 1 mole of calcium chloride means 110.98 grams of calcium chloride. So now we cancel our grams of calcium chloride. We have moles of calcium chloride. We move on to step 2. Step 2 is convert moles of calcium chloride to moles of calcium phosphate that can be made from it. This is going to use the balanced equation. Again, before you turn your brain on, just make sure you copy down the unit you're going to cancel, and then you know what to look for. Okay, I need the number that goes with moles of calcium chloride that will relate me to moles of calcium phosphate. That's what I'm trying to do here. So I'm looking for the balanced equation. And this tells me 3 moles of calcium chloride make 1 mole of calcium phosphate. So I put the 3 moles of calcium chloride and the 1 mole of calcium phosphate, and my moles of calcium chloride cancel. Last, convert to grams of calcium phosphate. The same as right here. We want moles of calcium phosphate on the bottom so that they will cancel. And then that is equal to 310.18 grams of calcium phosphate. I'm kind of running into my head here, but so now we just need to multiply. So I'll write my answer down here so I don't write it behind my head. And let's calculate. So 2.63 divide by 110.98 since it's on the bottom. Divide by 110.98. Then divide by 3 because it's on the bottom. So divide by 3. And then times 310.18 since it's on the top. Times 310.18 equals. And out of that I get 2.45 grams of calcium phosphate. Okay, so our limiting reactant was the calcium chloride. So we got 2.45 grams of the calcium phosphate. So we did not get this amount. What we got was this amount because there was not enough calcium chloride to make any more. Now, if we want the percent yield, I'm going to erase some of the stuff I put up here so I can make myself some space. I'll just do the percent yield right up at the top here. So my percent yield is going to be my theoretical yield, which was, or my actual yield rather, the part that I actually got, which was 1.53 grams of the precipitate, the calcium phosphate. But how much I theoretically could have gotten was 2.45 grams. 2.45 grams. And then I multiply it by 100% to make it a percentage. And let's calculate that. 1.53 divided by 2.45 times 100 equals, and we get to 3 sig figs, 62.4% yield. And so I know this was a very long problem. I wanted to give you one example of a really grand problem that could combine everything that you've learned in the last couple weeks. Of course, this is harder than most problems that I've posed to you, but I hope that was a good review of lots of the things that we've been learning lately, including stoichiometry here. So again, this is a week where you're going to have to do lots of practice. The lectures weren't too long. The practice is more important, okay? So make sure you do the homeworks. Make sure if you need more practice, try the in-book exercises as you're reading. Okay, and let me know if you have questions. And have a good week of studying. And I will see you soon.